Hey everyone, and welcome back. Today's explainer is all about a literal microscopic miracle that is happening inside you right now. We're going to unpack the incredibly complex, completely life-saving biological cascade of blood clotting. It is a rapid-fire emergency response system that's honestly just as elegant as it is essential, and we're going to map the whole thing out together. So think about it. What actually happens the very second you get a paper cut? To us, it's just a minor annoyance. Ouch, grab a Band-Aid, right? But down on a cellular level, it is a sudden, massive crisis. Your vascular system has literally just been breached. Without an immediate, hyper-fast emergency response, even a tiny scrape like that could lead to a severe hemorrhage, where you'd rapidly lose your entire blood volume. Your body has to react instantly. Okay, let's dive right into this. Here's our roadmap for today. 1. The river of life. 2. Stopping the bleed. 3. The clotting cascade. 4. Vitamin K and anticoagulants. 5. The cleanup crew. And finally, 6. When blood misbehaves. All right, let's kick things off with Section 1, the river of life, understanding our blood. So before an emergency even strikes, our blood flows smoothly, right? Like a peaceful river. But this river of life is surprisingly partitioned. Blood is technically a fluid connective tissue, and it's heavily weighted toward the liquid phase. Roughly 55% of it is plasma. That's an aqueous fluid made mostly of water that carries around all your dissolved proteins, hormones, and mineral ions. The remaining 45%, that's made up of the formed elements, which are essentially just your red blood cells packed really tightly together. But here is what's really interesting. There is this tiny whitish layer sitting right between the golden plasma and those dense red erythrocytes. If you spin a sample of blood in a centrifuge, you reveal this layer, known as the Buffy coat. It makes up less than 1% of your total blood volume, but man, it packs a punch. It houses your critical white blood cells and, most importantly for our explainer today, the platelets. These tiny little fragments, they are your absolute first responders. Which brings us to Section 2, emergency, stopping the bleed. Okay, so a vessel breaks. The peaceful flow is totally disrupted. Immediately, your body initiates hemostasis in 3 rapid-fire steps. Step 1, vascular spasms. The smooth muscles in the damaged blood vessel wall violently contract, sharply constricting the vessel just to slow down the blood flow to that area. Step 2, platelet plug formation, where platelets rush in to physically plug the hole. And then Step 3, blood coagulation, which is the formation of the actual permanent clot. Let's actually zoom in on that second step for a second. First, platelets deposit and literally adhere to the damaged vessel wall. Once they're stuck, they start secreting signaling molecules like serotonin. And get this, that serotonin actually helps maintain the vascular spasm we just talked about. It's brilliant. Finally, they aggregate. They clump together to form a temporary, albeit kind of fragile, plug that basically seals the breach for the time being. Let's move to Section 3. The complex clotting cascade. Now, a fragile plug is great for a split second, but it isn't enough long-term. We need the heavy machinery. During this cascade phase, the blood physically thickens into a gel-like clot, known as a thrombus. The absolutely crucial point here is how this works physically. The cascade ultimately creates a network of insoluble protein fibers called fibrin. These tough, insoluble fibrin threads weave together to form a literal microscopic mesh that drops right over the injury. It traps passing blood cells and massively reinforces that initial fragile platelet plug so it can actually withstand the intense pressure of your flowing blood. So, how does the body trigger this fibrin mesh? Well, it uses 2 different pathways. The extrinsic pathway is triggered by external tissue trauma, meaning damage outside the blood vessel. The intrinsic pathway, on the other hand, is triggered by internal blood trauma or if the blood comes into contact with a foreign surface. But the truly brilliant part is that both of these pathways converge. They join into a common pathway that takes a protein called prothrombin and converts it into an active enzyme called thrombin. And it's that thrombin that then generates our vital fibrin mesh. It's like a perfectly orchestrated biological symphony. Moving right along to Section 4, vitamin K and anticoagulants. Now, a biological cascade this powerful, it needs highly specific fuel and incredibly strict regulation. To build these clotting factors in your liver, your body absolutely requires vitamin K. And fun fact, that vitamin K is largely produced by the helpful bacteria just hanging out in your large intestine. It acts as the necessary fuel to prime these proteins for action. Because this cycle is so vital, modern medicine actually hacks it. For example, the drug warfarin purposefully blocks the reductase step in the vitamin K cycle, which severely reduces the synthesis of those clotting factors. This is a total lifesaver for patients who are at a dangerously high risk for thrombosis. And all of this beautifully illustrates the crazy, delicate balancing act happening inside your veins right now. You have clot formers aggressively trying to seal up a wound, completely balanced out by clot limiters, which are the body's natural anticoagulants. Molecules like antithrombin 3, protein C, and tissue factor pathway inhibitor are constantly on patrol. They are there to guarantee that once a clot forms, it does not spread excessively down the blood vessel, which could cause a fatal blockage. It is a biological tug-of-war. All right, Section 5, the fibrinolytic cleanup crew. Okay, so the bleeding has stopped, crisis averted. But now that internal scaffolding needs to be safely torn down. Healing starts with what we call clot retraction. That fibrin mesh actually contracts, literally pulling the damaged, torn edges of the blood vessel closer together. While that structural repair is happening, epithelial cells migrate right over the area, and a process called angiogenesis kicks off. That is the literal growth of entirely new blood vessels, stimulated by specialized growth factors to fully restore the damaged tissue. But what actually happens to the old clot itself? Well, enter the fibrinolytic system. You have an inactive protein called plasminogen that gets converted into an active enzyme called plasmin. Plasmin is your highly specialized microscopic cleanup crew. It carefully and safely digests the unnecessary fibrin mesh, lysing or breaking down the clot, and reopening the vessel to its full original capacity once the tissue underneath is completely good as new. And finally, Section 6, when blood misbehaves. Up until now, we've looked at the ideal scenario, but what happens when that delicate balance totally fails? First off, let's give you a quick medical hack to decode blood disorder terminology. It's actually super straightforward. If you see a medical term ending in penia, it just means a deficiency. If you see cytophis, it means an excess. So erythrocytemia simply means a dangerous deficiency of red blood cells. On the flip side, thrombocytosis would mean a massive excess of those clotting platelets.
One of the absolute most common deficiencies is anemia. This condition fundamentally diminishes the oxygen-carrying capacity of the blood, either because there simply aren't enough red blood cells, or the ones you do have lack sufficient hemoglobin. Without enough oxygen reaching your tissues, your cells literally cannot generate enough ATP for cellular energy. They also can't generate heat. And that is exactly why individuals dealing with anemia often experience severe exhaustion and a really intense intolerance to the cold.
Now, a particularly severe form of this is aplastic anemia. This happens when the actual stem cells in your bone marrow are damaged. We're talking damage often caused by external factors like heavy radiation exposure, industrial chemicals, or even certain medications. Because the bone marrow's production factory is effectively broken, the levels of all your blood cells drop dangerously low. This results in severe fatigue, chronic lingering infections, and a massive life-threatening increase in hemorrhage risk because you simply don't have enough platelets to form those vital plugs. So, as we wrap up this explainer, I just want to leave you with this final crazy thought. What would happen if this delicate balancing act in your veins suddenly failed right now? Every single moment of your life heavily relies on this microscopic emergency response system maintaining absolute perfect equilibrium. It is the only thing ensuring you don't bleed out from a tiny scratch or clot completely from a simple bruise. I really hope this breakdown has shown you just how fascinating and resilient your physiology truly is, and hopefully leaves you eager to uncover even more. Keep on learning, and I'll catch you in the next explainer.